en matemáticas, físicas y ciencias computacionales, y también estudió la parte de instrumentación industrial, mantenimiento e ingeniería. Es doctor en robótica y procesamiento pues, o maquinado de materiales de la Universidad de Lorraine, el Instituto Jean Lemore del CNRS, donde ese instituto está adscrito al Centro Nacional de Investigación Científica de Francia. Actualmente el doctor Usama se encuentra pues como estudiando y investigando en los tópicos de robóticas, programación industrial de robots de marcas como KUKA, FANUC y ABB. Vemos también que trabaja en la parte de diseño 3D utilizando diferentes programas de la parte CAD y CAM, como son el Autodesk Inventor y el SolidWorks. También trabaja en temas de manufactura y control numérico para el manejo de centros de mecanizado de 5 ejes. Entonces, en ese orden de ideas, su presentación nos va a permitir conocer esta otra parte del proceso. Vamos a contar entonces con su presentación, la cual es titulada Caracterización de procesos de manufactura pues como robótica, aplicación a los materiales pues como de maderas y esos procesos de transformación. Entonces, en este caso, esta última presentación, él nos la va a presentar en el idioma inglés, pues, que es pues como el lenguaje pues como que él entra a trabajar. Permítame entonces, yo le hago la introducción a Usama, pues en el respectivo, pues como idioma. Entonces, good morning, Usama.
For us, it's good evening now. We are in France. We are like 5 p.m. now. So good morning for Colombian people and good evening for European or Asiatic people.
Oh, yeah, thanks. We are very happy to have you today with us, and we want to invite you to start your presentation. So you can start.
Okay, so let me first of all share my screen up and check that everything is going well. Do you have my screen shared or not?
What's going on?
It's going on. It's okay? Up. Everything is okay or not? You can hear me, you can see the presentation, everything is okay, you can start?
I can see you, I can hear you, but right now I can't see your presentation.
Did you see my presentation now?
No, I can't see your presentation.
Okay, so let's wait a minute, it's always like this with video conference. And now you are seeing my presentation? Nice.
I can see. Oh yeah. Right now I can see your presentation.
You can see my presentation, but you can't see me.
Yeah, I can see you. I can see your presentation. I hear you very good.
Okay, I can start. So.
Yeah, you can start.
Okay, thank you. So let me first of all thank you for your opportunity to share science and knowledge with you. Special thanks to Professor Elizabeth Rodriguez for her invitation. Hola, Elizabeth. So I present myself. I am Usama Ayari, researcher in Lorraine University in the northeast of France. In these slides, I will present you a part of my PhD work realized with the collaboration of Mr. Nelson Pierjean and Mr. Boalianis. So, the presentation will be scheduled as following. I will start by explaining the context of the research work and its aims. After that, I will present the different devices and protocols used for experiences. Then I will show you the results and I will finish with some perspectives. So let's start with the research context. In the wood manufacturing industry, we find a lot of woodworking machines like conventional machines such as planer, numerical traditional machines like fanner. We find also the CNC router, which is frequently used for milling woods and which can be 3 or 4 or 5 degrees of freedoms. And we find also, but rarely, the industrial robots. Our work will interest in this kind of machines. So, talking about robots, it exists many times in manufacturing industry, such as autonomous robot, AIV. It means it's the abbreviation of automated intelligent vehicle, and AGV is the abbreviation of automated guided vehicle. As you see in front of you in the photo, there I present you a police robot. It's a robot used by the Tunisian government during the lockdown after the coronavirus pandemic. They use it to control citizens if they are respecting health restriction, if they are in good health, and a lot of other stuffs. So, second type of robots, we find also a service robot. As I present in front of you, the Asimo robot is frequently used in Japan, which can use it for example, like a waiter in a restaurant, like a barista in a bar, and most frequently in the retirement house in order to support retirement peoples and old peoples. And we find also industrial robot in their two structure, the serial structure and the parallel structure. Our job or our research will be interested in serial structure industrial robots. Concerning numbers, the installation of industrial robots has not stopped growing since 2005 and has accelerated with the appearance of concept of Industry 4.0 in 2011 and the trend to automate production line. These two factors lead to reach a number equal to 520,000 units of installed robots in the worldwide. The EFL is the International Federation of Robotics, forecast her statistics. Its statistics forecast like a 12%, almost a 12% increase in the number of robots installed in the world by the beginning of the year of 2021. But the appearance of the coronavirus, we don't know until now if it will affect this number or not. Maybe this number will increase, maybe this number will decrease. We don't know until now. With the coronavirus is changing everything in the world. So, concerning industrial sectors, we find industrial robots always, I am talking, in this part, the numbers presented concern always the industrial robots in their serial structure, like the arm robot, So, as I said, concerning industrial sectors, automotive field is always the first customer with 30% of the total number of installed robots frequently used in a lot of applications of tasks such as welding, assembling vehicle or car components, and machining materials like aluminum, iron, and a lot of other kind of materials. The electronics industry comes in the second place with 25% of the total number of robots installed in the world. They are frequently used to contribute in the handling and assembly electronic components, as well as the development of sensor networks. In the third place, the plastic and metal processing industry ranks in the third, as I said, in the third place in the world with a number of 10% of the total number of installed robots generally used for plastic machining or modeling applications. What surprised us, like people who are working in wood manufacturing, is that the wood industry is ranked in the last relation, in the last place in relation with the previous mentioned sectors. The percentage of used industrial robots in wood industry is not superior than 0.2% of the total number of robot installed in all over the world. So it's surprising for us. It's weird. So we start making questions about that. Why other sectors like automotive, electronics, pharmaceutics, aeronautic, they are using robots, and the industrial robots they prove is sufficient and is something suitable for production, for line production. Why we cannot use it for wood industry? So, by making our research and our state of art, we found like among the 0.2%, we find industrial robots in the furniture sector, in always talking about wood industry. We find it in furniture sector, such as at Schmidt. Schmidt is a big company here in France, specialized in construction of kitchens. They have like 40 robots for always arm robot. I am talking always about arm robots. So Schmidt has like 40 robots used for loading and unloading wood panels on cutting machines. There are also other applications such as at Bourgneuf, which use like they have a lot of arm robots used for painting furnitures. As far as wood construction is concerned, solutions are beginning to emerge. For example, with Emax Pro. Emax Pro is a company in Belgium, and it is a developer of robotic solutions for the wood industry. It has set up like a small other company called A2C, specialized in drilling, carving, nailing with arm robot, with industrial arm robot. But what is surprising for us, that there is no arm robot, there is no use of industrial arm robot for milling wood. This is the end of our research. So the goal or the purpose of our research is to use serial industrial robot for milling, which has many advantages, such as production. First of all, production is more flexible in case the manufacturer needs modifications of the product. The robot program can be changed and modified without stopping the production lines. Pay attention about this. Now, for people who are using like CNC router or other stuff, they need, if they want to change the program in order to personalize their product, they need to stop the production lines and to make modifications. But with the arm robot, the advantage is here with some concept called offline programmation of robots. We can change the robot program without stopping the line productions, which avoid us to lose money. The second advantage of using industrial robot or industrial arm robots for milling is a larger workspace in case the manufacturer needs to machine complicated shapes. So let me first of all explain what does it mean, a workspace for industrial robot. The workspace is the set of the point that can reach the robot in the space. Like for CNC router, it's like they can reach like lot of points which make a shape of square. But for arm robots, we don't have a specific shape of the workspace, but the definition of workspace is the set of numbers that can the robot reach in the space. So this is the second advantage. Imagine with me, for example, if we need to mention a complicated shape or a complicated morphology of wood piece or other material piece. So the robot has more flexibility to reach a lot of point in the piece or in the sample. But with the CNC router, we are limited in the degree of freedom. So this was an example. The third advantage is we have lower production cycle time. Of course, with robots, As I said, if we can change directly the program without stopping lines, stopping the line of productions, we can earn time. And earn time, it means earn money, earn dinero. So, but unfortunately, these adventures are faced by a lot of constraints, which the most important of them is when the tool remove materials, important cutting forces are created, which cause toolpath deviations, and the consequence, we will get low machining accuracy, and the machined surface will be so bad. So, the target of our research is to characterize the cutting forces during wood machining with arm robot. So, in other terms, we want to understand the phenomenon. We want to know those cutting forces in order to manage if there are big or an important cutting forces, if there is solution to reduce them or to reduce the toolpath deviations. So now, after I explained you the context of this research, the purpose or the aims, let me present you the devices and protocols used for experience, for making experience. First of all, and this is the most important device that we use, our experimental bench is composed by a poly-articulated or an anthropomorphic or these terms all these terms are the name of an arm robot. We can call it poly-articulated arm robot or anthropomorphic arm robot. Its strength is KUKA KR 210. It has 6 degrees of freedom. The last 3 axes of the robot are concurrent and allow to emulate the moves of hand wrist, as you see here in the last axis 6, 5, and 4. They are concurrent. Their axes they are concurrent, and they emulate the moves of human hand wrist. And the first 3 axes, axis 1, axis 2, axis 3, they serve like positioning this wrist hand in the space of the workspace. So, with the robot, we have like an attached high-speed spindle, used, of course, to rotate the tool, and the measurement obtained during machining wood with a KUKA robot are compared to ones obtained by CNC routers, always in the same experimental conditions. So, why, maybe you are asking now, why we want to compare with CNC router our results. So, as I said, CNC router now is frequently used in wood industry, and you know, using our robot is intuitive now, is something new, is not common. So we take like the results coming from the CNC router machining as a reference, and we will compare with the results obtained by machining with the robot. Next, of course, to measure the cutting forces, we need a cutting forces sensor. So the experimental bench is instrumented with force sensor Kistler to measure cutting forces. The signal is amplified and converted then to numerical signal with an analogic to digital converter, which the sampling frequency is 2 kHz. The results after are displayed on computer through an acquisition model developed in University of Lorraine. As the materials to mention, our choices are oriented to MDF, medium density fiber. First of all, for its properties of homogeneity along the axes X and Y. The second material that we choose to mention is beech, chosen for its heterogeneity and because it presents the reference material for wood machining research. The third material is fur, which is chosen for its heterogeneity, and because it has in each texture, it presents knots and a lot of irregularities. The knots is, we call knots those black holes here, or black points here, or black marks here, and our choice is oriented to use fur because it has a lot of such kind of irregularities. So for the practical, in the total, 30 samples for each material are machined with a feed rate equal to 1000 millimeter per minute. Two grooves will be realized. One horizontal groove presented in this photo, and the second groove is, we call it vertical groove, presented in this photo. For machining, we choose two configurations inspired from a stiffness map of a similar robot cooker. So first of all, let me explain what does it mean, stiffness. Stiffness, or robot stiffness, is like we can explain it to rigidity of human hand resistance. So for example, to handle a chair, for example, your hand doesn't apply the same force when you are taking the chair like this, or when you are taking the chair like this, or when you are taking the chair like this. The hand doesn't make the same effort, doesn't apply the same effort, and each time the resistance of the hand, or the force of the hand, is not the same. So it's similar to the robot. It has rigidity, it has force, it has like a ability of resistance. So for machining, we choose two configurations inspired, as I said, inspired by or from a stiffness map of a similar robot, not the same robot. It's this stiff map is built by Clergyma for a robot, but Kuka is for a Kuka robot, but another reference. It's not the same reference as our robot. So we use this stiff map to define two configurations for machining. The first one called stiff configurations, where the end of arm tool is 1.3 meters far from the robot base. This position is frequently used for drilling or nailing, and we find it a lot in the industry. The second configuration is called flexible configurations, where the end of arm tool is situated at 2.6 meters from robot base. These configurations is chosen to see what happens when the robot undergoes forces on its workspace. In other terms, why we put the robot in such configurations at 2.6 meters from its base? Because we want to know, we want to answer our curiosity to see when the robot is on its border, or in the limits, as you can see, in the limits of its workspace, what will happen if we apply forces there? What will happen to its structure? What will happen in the level of its articulations? So this position is chosen just to answer our curiosity, how the robot will behave when it is on its limit, or on its limit of workspace, and applied forces, and important forces are applied on its arm, or on its end of arm tool. So to verify, in order to check robot stiffness, as I said, the stiffness map before is not for the same robot. It's for Kuka robot, yes, but not the same reference. So this is why we make an operation to check robot stiffness. So in order to check robot stiffness behavior, in the two configurations, we used finite element modeling methods by applying a force equal to 500 Newton on the end of arm tool. And after that, the results are the displacement of the robot. So the results shows in stiff configurations, the robot moves by a distance of 0, as you see here in the table, Always displacement, I will show displacement due to a force of 500 newtons in the y-axis. Why the y-axis? Because it's the tool path when we are meshing. So the results show when we are in stiff configurations, by applying a force of 500 newtons, the robots move by 0.6 millimeters. In the same experimental conditions, with 500 newtons, in the flexible configurations, we register a displacement or moves of 1.5 millimeters. So, those results confirm our hypothesis that the robot is less resistive when the end of arm tool is far from the robot base. So this one will affect a lot after that for the catching forces. So now to summarize the part of experimental devices and the protocol, I will show two videos that illustrates the machining operations. Okay, the first one, I will reduce, okay. The first one consists to matching wood on stiff configurations and show the interface. As you see here, this is how we measure the cutting forces. This is the interface of measuring cutting forces. And we always start by calibrating the sample in order to avoid simulations errors. And after that, we make the groove. As a reminder, always the feed rate is 1000 millimeters per minute. So this is the first video. The second video is like the same machining operation, but with a zoom and a slow motion. As you see here, always we are grooving. This is what we call it the force, the cutting forces sensor. Let me repeat. It is linked to an amplifier and analog to digital converted, and after that, the forces are displayed on our computer. Okay, let's pass up. Now, after explaining the experimental bench as well as the follow-up protocol, let's see together the results. As a reminder, we will compare, as I said, we will compare cutting forces measured with CNC router and the robot on its stiff and flexible configuration for three wood materials: MDF, medium density fiber, beech, and fir. For the MDF, as you can see, the measurements show different average of cutting forces. The variations are intensified by changing the meshing from CNC to robot and the meshing configurations from stiff configuration to flexible one. The same trend is found in beech machining, where higher catching forces and fluctuations are measured due to the heterogeneity of the material and its high density. Same with fir machining, the measurements obtained vary depending on the machine and its configurations. The main finding is that machining in stiff configurations produces cutting forces that are about half the values obtained with almost the half of the values obtained with the CNC router and the robot in a flexible configuration. In order to explain this phenomenon, we did what we call the spectral analysis of acquired signal of MDF, and we found the presence of harmonic frequencies with CNC router and the robot in flexible configurations. So, what I called harmonics is those part of frequency. Only with CNC router and with MDF machined in flexible configuration, we found those kind of harmonics. However, these harmonics are absent on the frequency spectrum of the robotic machining in stiff configurations. This led us This leads us to believe that there is a loss of energy and that the robot in stiff configurations absorbs the machining vibrations. The same results are found with beach and fear. After that, always to answer our curiosity, we machine beach perpendicularly to its fiber direction. In the first experiences, we did the groove parallel. We did the groove, like we machined the groove parallel to wood fibers. Now we changed the direction of the machining tool. Now we will machine perpendicularly to wood fibers, and what we notice that tangential and radial cutting forces increases 8 times higher than the measurement obtained after horizontal groove. In other terms, when we have beech or other wood that contain fibers, it's not like MDF. In MDF there is no fiber, there is no line. But in beech, in fir, there is lines. When we are machining parallel to the fibers, we are 8 times less than when we are machining perpendicular to wood fibers. Otherwise, in other terms, let me explain. When the robot is machining perpendicular to the wood fibers, it needs to exert or to apply 8 times more cutting forces than the ones measured when we are machining parallel to the wood fiber. After that, we wanted to see the notes effects. As I explained, the notes they are the irregularity which we can find frequently with fur. So we want to see now in this experience, we want to see what will happen in terms of cutting forces when the tool enter or machine those kind of notes. So as a result, we machine it, for example, by passing the tool through those notes. The obtained results reveal when the tool machine a note, the cutting forces undergo a sudden, surprising or a sudden and significant increase that can reach the double of force out of note. As you see here in this photo, here we are out of the notes. Here it's related to this part. The tool is out of the notes. Okay, we have such cutting forces like almost 100 Newton. But when we enter here in the notes, we have like a significant increase of cutting forces, which can reach the double of forces registered out of notes. So this is the effect of notes. After that, a sudden change of those cutting forces generates significant damage. As you see here, the damage when the cutting forces are suddenly increased, we can see a lot of damage like splinters, as you see here, cracks or fissuration. We can see also defibration marks. So now I will finish with some perspectives. At first one, our purpose and our goal for the next step, we will gather a robot model with measured cutting forces and inject them. The robot model is developed on MATLAB, and the measured forces are obtained with the instrumental line. So both of them, we will gather them and we will inject them on MATLAB Simulink to do what? In order to create a new robotic control depending on measured cutting forces. I will explain, I will give more details here. So now we have our model. We'll start by modelizations of the robot in MATLAB. After that, we have the measurement of cutting forces when the tool is removing materials, of course, wood materials. So now we will gather both of this. We will inject them in MATLAB Simulink in order to what? In order to create a robotic control that make the robot able to adjust its position during machining. In other terms, when a robot is using, the sensor will send the cutting forces to the robot control that there is a high cutting forces, and the robot will understand that there is a high cutting force, and immediately, instantly, the robot will adjust its position in order to respect tool path and in order to increase or to improve machine surface quality. So the purpose of after all of this one is adjusting the moves of the robot when it is machining wood. This is the first perspective. The second perspective is a little bit special. So to answer to our curiosity, we will change machining concepts. Let me start the video. So as I said, we will change the machining concept. The simple and the force sensor, as can you see here, the sensor and the sensor and the samples are attached to the end of arm tool, and the spindle will be fixed in the ground. This experience has like purpose to see what happened in terms of cutting forces and robot vibration on its articulations. So maybe it's good for you to attach the symbols and the cutting forces sensor in the robot. Why we do not simplify the stuffs and machine the wood above the table like normal experience? Why? Because some industrial people, like industrials, they asked us, maybe we can they can improve their company environment, technical company environment, by putting the robot in the middle of a lot of machining devices, and the robot will take the piece of wood and we make machine number one here, grooving, for example, and after that, drilling, nailing, other operation. So they said to us, let's see what happens in terms of cutting forces when we imagine that the robot is in the middle, in the center of a lot of machines, and the robot take the machine with the gripper, take the wood piece with the gripper, and starts displacing this samples or this wood piece from machine to another one. So this is special, this is new, and our perspective now to see what will this concept give in terms of cutting forces and of course accuracy and machining quality. So thank you for your attention, and for more information you can visit my YouTube channel. It's not a professional YouTube channel, it's for my pleasure, where I share knowledge and science. And for people who are interested to know more about how we modulated the robot, more details about the finite element methods, you have here the reference of my paper. You can download it from ResearchGate, and you can find everything you want. So thank you for your attention. Let me up. Okay.
Well, Osama, thank you so much for your presentation. Right now, we're gonna make you some questions. First of all, we have a question from Norma Guarnizo. We say something like, in which direction were generated higher forces when you were studying cutting in knobs? In which directions were higher forces when you are machining the knobs? I don't know, when you were drilling or were
grooving. So when we did the operations, the groovings in notes, The objective was to see how the cutting forces behaves out of nodes and in the nodes. So it was, it was for purpose. We put the simples. It was the purpose. We wanted the machine starts out of nodes like normal wood, and after that, in the end of operation, we will get the catching forces. We are sure here that in the end of the catching operations, the tools were in the nodes. So maybe, for example, you can find the nodes in the middle of the samples. So here, when we get the results of cutting forces, we are not sure where exactly the cutting forces are related to the nodes. So it's for purpose, we put always the nodes in a direction in the end of cutting operations in order to be sure that cutting forces acquired after that they are the cutting forces of nodes, but not for other part of the simple. I don't know if I answer very well to your question or not.
Okay, no, I think I can get that. Another question. Do you study drilling operations, the forces produced by drilling operations?
For drilling operation we did, but for drilling operation you are not removing a big quantity of materials. So the cutting forces, like here we find like cutting forces between 100 and 300 or 400 Newton, but for drilling it's like 10 Newtons, 20 Newtons. There is no need to measure it because it will not influence, it will not affect the tool path, because there is, when you are drilling, you are not removing a lot of quantity, and the tool is not very well immersed in the material, so doesn't matter. But when you are grooving, the tool, is immersed. It's like in the sea, is immersed in the material. So the cutting forces are important. So we can measure, we can characterize something from that.
Okay, thank you. Well, there are something I want to ask you too. When you were talking about the two possibilities of the experiments, there were the flexible, that was when the arm were fully extended, and the other one was when the arm were retracted. In that way, I know that sometimes it's not recommended use the arm fully extended, because there are some singularities, because when that is in this position, the robot doesn't know if he's gonna start movement in this side or in this side. How do you proceed with that? Microphone. You're.
Okay, so it's in purpose. I didn't mention singularities because if I mention it, I will explain. So first of all, if robots is in singularities, it will not move. It will refuse the command. So how we will manage it? So first of all, why we search. Why we put the robot in the limits of its borders and started machining there. It's like to answer to our curiosity. What happened in terms of cutting forces and especially stiffness, robot stiffness, if we are applying forces in the limits of its borders. It's like we are taking the machine or taking the robot to its limits to see. Of course, we will not destroy the robot, but we want to see what happened in terms of cutting forces and vibrations when the robot is receiving applied forces in the end of its or in the limits of its workspace. So other purpose is to see how robot behave when you are near to singularity. Of course, here we are not in singularity. As I told you, the robot refused to move when it is in singularity. And what we did for that, we approach, we get near to singularity, and we started exciting, and giving cutting forces and applying forces to the robot to see how it will behave. So I agree with you. It's rare to find people who are machining in that kind of distance. But as I told you, I totally agree with you. But as I told you, for example, imagine with me like you have a robot and circuit with a lot of machine. I explained at the end of my presentation. So now, like an industrial person, he asked us, let's see what happened with that. Imagine like, for example, you have a lot of machines, but you don't have a lot of places, and you are obliged to put a machine a little bit far from the robot base. Now we'll be near to the case of the robot when it is near to its limit. So for us, we want to search and to see how the robot behave when it is on its limit. Like for example, for persons who can only run 10 kilometers, we want to give them a heavy back in the last kilometers to see them what will do. How they will behave. Like we are searching the limit of robots, of course, with taking the precaution or with paying attention to not destroy the machine. It costs like 180,000 euros. You will not destroy it, but we are searching how it will behave, what we'll do. We are imagining like the concept that I explained in the end of the presentation. Imagine, people they are putting a lot of machines and they don't have a lot of space, and they are a little bit far from the robot base. Like this, with this result, they will understand that the more they are far from the robot base, the less robot is rigid, and the less accuracy is, and the less surface quality is good or is nice. So the more we are machining far from the robot base. People who are asking for this concept, when you are circuit the robot with machines. So when you are far from the robot base, you will lose stiffness, you will lose rigidity. So if you need to have like good machined surface, a high machining accuracy, you have to choose very specially and very precisely your robot position. It's not random robot position. There is a specific robot position that gives us the maximum of rigidity and the maximum of accuracy. This is why we wanted, to show the difference between this case and this case.
Okay, can you give me a minute? I'm going to translate some of the questions for the field, because here in Colombia we speak Spanish, and some of the people who are watching the video don't have a high level of English, so I'm gonna translate some questions and the answers that you give us, and I'm gonna come back with you in a moment. Okay? Bueno, entonces se le hicieron pues como un par de preguntas a Usama. Una de ellas es si habían estudiado el tema de los procesos de perforación, puesto que en algunos casos, puesto que el estudio que pueden observar solo estaba presentando estudios pues como de perfilado en los procesos pues, de mecanizado, nos indica entonces que en ese caso optaron por esos procesos de perfilado en vez de los procesos pues como de taladrado, por ejemplo, puesto que en los procesos de taladrado las fuerzas a las cuales se ve sujeta el robot son mucho más bajas, entonces no entran a ser tan significativas para el estudio pues como que estaban realizando, porque entran a ser de unos niveles mucho más bajos. Por otro lado, otra de las preguntas pues como que estuvo pues como ahí en cuestión era ¿Qué ocurría entonces cuando el robot estaba como trabajando cerca de sus límites? Puesto que el robot está compuesto por una serie de articulaciones, no es adecuado que esas articulaciones estén completamente alineadas, puesto que en las condiciones en las cuales ellas están pues como completamente alineadas y ella va a tener que hacer un movimiento, a ella le va a costar saber si la mejor ruta para desplazarse hacia un punto va a ser hacer el movimiento en este sentido o hacer el movimiento en el sentido contrario, porque están en esas condiciones de singularidad. Entonces, que siempre estuvieron evitando pues como esas condiciones de singularidad, sin embargo, están tratando de estudiar todos aquellos pues como condiciones pues como adversas de operación, sin embargo tampoco sin llevarlo tan al límite por los costos tan elevados que tienen este tipo de robots y pues tampoco es conveniente pues como afectar el presupuesto de los procesos de investigación pues como de esa forma. Voy a revisar si de pronto hay alguna otra preguntita. Listo. Listo, no. Usama, the other comments on the YouTube were so grateful. We are also so grateful with you because you come here and talk us about your investigation process. We're gonna finish in this way for this part, this symposium, and we are so pleased to have you this day.